Okay, good morning. We have been talking about interface advection techniques in the previous lecture, and today we will continue the discussion on the same. So, if you recall, we discussed that if we have to advect color function, then how we can solve the transient advection equation, and then if we do approximate the fluxes of the color function using the piecewise constant scheme, then this is what solution actually we were obtaining. Now there can be some confusions in our mind that if we say further decrease the value of delta x, or if we change the value of time step, then what will be the effect on the parameter. So to do so, what we have done, this is a Python code which is written for this particular problem, and here you can see that first is the effect of the grid size. Okay, so in terms of effect of grid size, what is done, first, whatever the slug is considered, that slug is only having 10 elements in this thickness. Okay, so I should not write 10 delta x, I should only write that delta x is selected in such a way because length is fixed, so that it contains only 10 elements, okay, or 10 cells. And whenever the second graph is made, then corresponding to this, now the number of small elements inside this are 20, in third it is 30, and in last it is 40. Okay, so now you can see that the one which is having least number of cell size, corresponding to that, in the initial condition you can only see, because cell size is larger, so one value which is here, that is having value 0, and the next value is 1, but this difference, this cell size is large, delta node to node distance is actually large in this case because of the less number of divisions or same length of the slug. So because of this reason, you will be finding that it appears little bit tilted. Okay, whereas our original interface is actually straight. So it means that if my grid size in case of multi-phase flow problem is not sufficient enough, then from the starting itself at t equal to 0 itself, we will be having certain amount of error. Okay, in actual practice, this should appear like a straight theoretically because it's a slug, but if your grid size is large, so at the initial point itself you will be finding some amount of error. And whenever you are increasing the number of divisions, if you are increasing number of divisions, what it means, you are decreasing the cell size. Okay, so when the cell size is decreased, then of course you can now observe that this distance is small, so that's why 0 to 1 angle will be actually less. Okay, and as we increase the cell size to 30 number of divisions, 40 number of, decrease the cell size by increasing number of divisions inside the slug, we can see that this initial times our slug definition is becoming more identical to the theoretical one. Okay, now you can see whenever I am trying to calculate the solution, so in all cases what I have done, I maintained delta t as nothing but 0.5 times of delta x. Everywhere time step is maintained 0.5 times of delta x. So that's why dt in all the cases will be different, because delta x in first case is large, so that's why dt is large here, whereas delta x in this case is small, so dt is small over here. Okay, now you can observe that whenever my cell size is large, corresponding to that at the same time 3.5 and 7, I can consider at 3.5 my spread is slightly less in comparison to the spread at the 7. Okay, whereas the peak value is actually decreasing. On contrary, if you compare this figure with the second figure at same time instance, what you are observing, you are observing that the peak, which is peak in volume fraction, which is observed for 20 number of divisions, that is large, and this dispersion is also little bit less. Okay, here again with reference to this, peak is large and dispersion is less. Okay. Likewise, whenever we have decreased whenever we have decreased the cell size further by increasing 30 number of divisions, again we are observing this effect. When we went from 30 to 40, you can see that in the peak portion, now instead of becoming this like this, it is actually widening at the top during the initial times. Okay, so it means whenever we are decreasing the grid size, then our spread is actually decreasing. Okay, and here you can see this is the difference in between cell size of 40 and 50. Now if you compare the result in between 40 and 50 by plotting both the graphs simultaneously on a single plot, you will be observing that the difference between these two will be very less. Okay, so it means that after going beyond a certain limit of number of divisions within the slug, your solution is trying to become grid independent. Okay, after that, whatever number of divisions you increase within the slug, your result is not changing ultimately, and at the same point of time your result is not changing and your result is also not physically correct. Is this point clear? So two things we established over here, because whenever for the first time I have shown you this plot, you may have this confusion that till now we have not varied the number of grids. Okay, so once we vary the number of grids, we observed that going from very coarse mesh to finer mesh, of course there was change, but after a critical limit, even if we are making mesh further fine, then we are not experiencing any significant change in the outcome. However, upon further refining the mesh, whatever outcome we are obtaining, that is also not physically correct. So it means that whatever the conventional upwind or piecewise constant scheme which we were using for single phase flow problem, that does not work well when we do talk about the advection of the volume fraction. Okay. Now same thing can also be seen in terms of the effect of time step. So you can see that in all these three cases, the grid size is maintained 20 delta x only, okay, within the slug. But what is done in first case, delta t is considered 0.25 of delta x, in second case it is 0.5 of delta x, and in third case it is 1.25 times of delta x. Okay, so you can see that in the first one, whenever your time step is very small, so normally what is our tendency? Sometimes our tendency is smaller will be the time step, more accurate will be or more stable will be the solution. Typically that comes always to our mind. But here you can see that whenever for the same grid size I maintained delta t equal to 0.25 delta x and 0.5 into delta x, you can see when we are going with 0.5 into delta x, then relatively our spread is actually narrow, but when we are going for very small, then spread is more. Okay, and on contrary, in both the situations our solution is actually stable. In both these cases solution is stable the moment I maintain. So yesterday I told you one simple thing, that whenever we do select the time step, we select in such a way so that u naught into delta t has to be less than equal to delta x. So why this thing is I mentioned, because you can see that when I maintained delta t equal to 1.25 into delta x, you can see what is your solution. Okay, so here it is seeing that this solution is actually oscillatory, and of course I have not changed the bounds, but it is going out of the bounds of the volume fraction value. So typically our volume fraction value should stay between 0 to 1, but it is, you can see the solution is becoming unstable, unbounded, and it is going beyond the values of 0 and 1, and the nature of solution is actually oscillatory. In one grid size it is coming very small, and in other grid size it is increasing significantly. Okay, so here we can see that by changing the time step, the concept of stability can be established, stability and boundness of the solution. Okay, so it was very clear to us from these. What you can do, I'll provide you the copy of this Python code, so you can try, and by changing different delta t and delta x, you can give a try. Now, next part is what we need to do. We have seen that by giving multiple trials, even upon refining the grid size and the time step, we are not getting good results. So what should be our next attempt? Our next attempt should be to improve the scheme. Okay. So in terms of improving the scheme, now our next attempt is, instead of considering the piecewise scheme, now we are considering linear upwind differencing scheme. Okay, so in case of linear upwind differencing scheme, what we are doing, within each computational cell we are defining some slope. So here you can see in cell j minus 1, the value of this slope is sj minus 1. Okay, and in next cell the value is sj. Okay, so what we are doing now, earlier what we were doing, we were defining this with a horizontal line. Okay, depending upon the amount of the volume fraction, we were choosing this line in such a way so that it's a horizontal line and it covers the fraction of area equal to that of the volume fraction of the primary fluid. Okay, but now instead of this, the attempt is that we will be considering a linear slope. When this linear slope will be advecting with time, what will be happening? This point will be transporting to this new location. All are clear with this point? So now, when it will be translating with this, then this much addition of new volume has taken place. Okay. If you were moving with which one? If you were moving with what? Constant, then the volume added would have been this much. Okay, now volume added is slightly less. At the same point of time, because of this next slope, this line will be occupying after time step delta t this new position. Okay, so here also, instead of large amount of volume going, a small quantity of volume is actually leaving. Okay, so it means that we have not maintained still the 100% accuracy, because when 100% accuracy will be maintained, if my scheme is able to behave in such a way so that upon the transfer of flux, first this cell gets completely filled with volume fraction of 1, and then the spillover of the fluid starts to the next cell. Okay, any scheme which is able to ensure that, that scheme will be obviously 100% accurate. Okay, but in this case also, what will be happening, part of the volume is going, but what was going with piecewise constant scheme, in comparison to that, the flux leaving across the boundary is actually less. All are clear with this point? So it means that this scheme may appear to be slightly better than the piecewise constant scheme, but still this scheme is not 100% accurate. Okay, now the point is, if this is not 100% accurate, then why we are studying this scheme? So the reason is because whenever we are trying to solve numerically the solution of equations, we are not going for exact solution. Our attempt is to solve the approximate solution, because already we have made approximations in the equations once we have discretized these. Okay, so the point is that upon approximate solution, if any scheme provides solution very close to the exact solution, that scheme will be actually serving our purpose. Okay, so let's attempt this one. So using this scheme, of course, what you need to do, you need to do some mathematical computations, and if you do mathematical computations, you will be finding that the flux at left face, particularly at this phase, can be given as Cj minus 1 at time step n plus delta x minus u naught delta t into Sj minus 1. What is Sj minus 1? The slope of this line. Because now when volume is translating, it is translating like this. So we need to multiply the slope with the linear distance which is covered. Is this point clear? So total cell volume is, total cell length is delta x, this much is u naught delta t, and if I consider that Cj minus 1 was the full length, then it will be Cj minus 1 n plus delta x minus u delta t. This particular portion I am taking minus with this slope Sj minus 1. All are clear with this idea? Now, after that I am multiplying it with how much distance actually we have moved, that is u naught into delta t. So this is simple mathematical equation. What you need to do geometrically, you need to first plot these as two different time levels, and then you need to take the difference of the volumes. If you take difference of volumes, this will tell you how much amount of volume has shifted from this cell to this one, and that volume is actually we have estimated in terms of flux moving from this left point. Okay. Likewise, if you calculate the flux moving from the right point, that will be Cj n plus delta x minus u naught delta t, and it will be slope of this cell, slope of the cell in the upwind direction. So when I am calculating at this cell, slope will be Sj divided by 2 into u naught delta t. Okay. Now if you substitute these values of f at j plus 1 by 2, sorry, j minus 1 by 2 and f at j plus 1 by 2, and in order to f this entire you need to multiply with u naught. Okay. So now if you consider these two to be your fluxes, then ultimately you will be getting your final equation will become Cj at n plus 1 equal to 1 minus lambda Cj plus lambda Cj minus 1 minus delta x by 2 1 minus lambda into lambda Sj minus 1. Where lambda we have defined as u naught into delta t by delta x. Is this point clear? So this is the equation which can work if we are considering nothing but linear upwind scale. Okay. Now what you can do, it is important that all other parameters we know, but this Sj is something which is coming as a new parameter into our formulation. So how to calculate the value of slope? So value of slope, you can see Sj plus. What is the meaning? Sj plus is J plus, they are referring to the rightward face. So if you have to calculate slope at the rightward face, it is simply taken as the value of volume fraction in J plus 1th cell minus at jth cell divided by delta x. Okay. Likewise, Sj minus is taken as, which is at this point, volume fraction at this point minus volume fraction at this point divided by delta x. Okay. So now what I estimated, I have estimated two slopes. One is Sj plus, which is at this face. One is Sj minus, which is at this face. But I need to define the value of Sj and Sj minus 1. So to calculate the value of Sj, what we are doing, we are taking the weighted average of the slopes which are obtained at the cell faces. Okay. So weighted average 1 minus kappa by 2 Sj minus plus 1 plus kappa by 2 Sj minus. So when my kappa will be equal to 0, corresponding to this I will be giving equal weightage to right face and the left face, and my slope at the center will be nothing but equal to the average of the slopes at the cell boundaries. Okay. But if I take value of kappa less than 0.5, then I will be giving more weightage to the previous cell. If I take value of kappa greater than 0.5, then I will be giving the weightage to the rightward cell. Is this point clear? So now the Python code which I have done for the constant piecewise constant scheme, that I will provide you. In that code only you need to do two additions. One addition is you need to use this equation, and then along with this equation you also need to do extra calculation of Sj. And for calculating Sj, first you need to define the grid of Sj which is at offset of delta x by 2 from the central nodal values. Okay, because this will be then utilized to calculate J plus and J minus. Once you calculated J plus and J minus, then on your actual node where volume fraction is stored, there by using this weighted average actually you can store the value of. Is this point clear? So probably because one code already I have shown you, so I will be giving you that Python code, you can try that, and if you want pseudo code I can explain to you, so that you can, if you don't know Python, then you can try it in any other language, say MATLAB or C++ or whatever you are comfortable with. Okay, but what you can do, you can try this equation with that particular code. Okay, so if you try, what you will be finding? You will be finding that upon using this scheme, now solution is bit okay, but this is having so many oscillations. Okay, so these are the oscillations you can see. Now this red colored line is the solution corresponding to value of k equal to 0. Okay, and this one extreme is corresponding to k greater than 0 and one extreme is corresponding to k less than 0. Because to whichever direction you will be giving the more weightage, that direction will try to peak the value of volume fraction towards that particular side. Is this point clear? So here again our expectation was, because it was very clear to us at the starting itself that this scheme is not giving us the exact outcome, but because in numerical simulations we work with the approximate solution only, so our idea was that we will give a try, and if say it is giving solution close to the theoretical solution, probably we can go ahead with this scheme. Okay, but when we tried this, we obtained that it is giving actually oscillatory nature of the solution. So if you consider that this solution is not oscillatory, then to maximum extent you are able to approximate it closely. Okay, you can see this black line and this line spread is not much, and even at the initial time and later time your solution is not much diffusing, like it is not transferring much to the large number of grid size, large number of grids upon progression of the time. Okay, it is slowly, it has of course transversed, but not much. Okay, so it means, but the only issue with this type of solution is that it is having significant oscillations. Okay, so it means that linear upwind interpolation will also not be serving the purpose for advection of the color function. Okay, and all these results whatever are plotted over here, you can give a try. You have to simply code the portion which I have explained. Okay, so what we need to do now, we have to go ahead with something else. We need to decide something else. Okay, so now the solution to this is seen in terms of the volume of fluid. Okay, so what is typically done in volume of fluid method, it was decided in volume of fluid method that whenever we were using the color function, ultimately what we were doing, so we were not taking into account the normal direction of the interface. We were simply, with reference to the horizontal axis, we were simply representing a line which was specifying the corresponding volume fraction in a particular cell. Okay, now instead of using this scheme, what I will do, first I will check that in my original situation, if this is fluid 1, this is fluid 2, I will first check where my normal is pointed to the interface. Okay, so how I can calculate normal? Gradient of color function divided by magnitude of the gradient of color function. This will be giving me nothing but the outward normal, unit normal. So here you can see that at every point I have 1 and here it is 0. So in which direction this gradient will be? In this direction. So this is my unit normal vector. All are clear with this point? So basically, in case of volume of fluid method, in first step, from the initial given color function field, the normal direction to the interface is estimated. Is this one clear? After the normal direction to the interface is estimated, then in a computational cell, your color function is specified in a plane which is normal to the direction of outward normal to the interface. Okay, for example, if your normal is pointing in this direction, what will be the plane normal to this outward normal? This will be the plane. Okay, now in my grid, I will be placing the volume fraction line in this way. Okay, but where to place, whether at this point, or at this point, how we can decide? This we can decide. We need to place this volume fraction line in such a way so that it is covering the area equal to that of the area of the fluid one in that particular computational cell. Is this one clear? So now you can see that up to Cj minus 1 my volume fraction value was 1, and from j plus 1 onwards this volume fraction value was 0. Okay, but this was the cell which was earlier having volume fraction something like this. Okay, now instead of representing this line in a horizontal manner, first I estimated that where my normal is pointing. So normal is pointing in the which direction? Rightward direction. So that's why I should place this line in the vertical axis so that the normal is facing in the normal to this particular plane. Okay, and of course where to place this, that will be depending upon the area. If Cj value is 0.1, then it will be coming somewhere here. If it is 0.9, then it will be coming somewhere here, depending upon the area it is occupying in the plane. All are clear with this point? Now you can easily understand that whenever your cell will be moving through this much distance, what will be your flux at the right boundary? Flux at the right boundary of cell should be, what should be flux at this point? When your time step is moving the interface through this distance, up to this time, what should be the flux? Please tell me. Up to this point, anything should move through the boundary? Should color function move across this boundary? Whenever it will be moving in a rightward direction, flux across this cell, when it will be coming? Say this is having u naught velocity. Okay, so up to this point, say this distance is how much? This is a one-dimensional cell. So if this is delta x, can I write this portion to be Cj into delta x? All are clear with this point? And how much will be this portion? 1 minus Cj into delta x. Okay. My u naught, what will be u naught into delta t? U naught into delta t will be the total distance moved by the interface. Okay, this will be the total distance moved by the interface. You have to understand this point very clearly now. If your u naught into delta t is less than 1 minus Cj into delta x, what it means? What it means? Please tell me. U naught into delta t is less than 1 minus Cj into delta x. What is 1 minus Cj into delta x? This distance. Okay. So when u naught into delta t is less than this distance, then any color function should pass through this boundary? No, because ultimately this entire will be lying in the previous cell only, and whatever the zero color function value is, that will be only displaced across the boundary. Okay, so that's why you can see over here fj plus 1 by 2 dt with its integration from t to delta t will be 0 when delta t is less than equal to 1 minus cj delta x by. All are clear with this point or not? Okay. When your u naught into delta t is greater than 1 minus cj into delta x, then what will happen? For the duration 1 minus cj into delta x, flux through this should be 0, and after the distance traveled is in addition to 1 minus cj into delta x, for that much duration flux will be coming equal to 1. All are clear with this point or not? Okay, so that is the reason now you can see that this flux is okay. Geometrically, first you tell me what I am saying over here. Please try to understand this. It was here. Okay, this distance is how much? 1 minus cj into delta x. Say the total distance moved is u naught into delta t. This is this much. Okay, then this distance will be how much? U naught into delta t was the total minus 1 minus cj into delta x. Is this one clear? So you can see that in the initial portion, whenever your interface will be traveling, corresponding to this flux should be 0, but flux should only come into picture when your distance is or your interface is moved through this cell. So it means only in this portion your flux should come. Okay, so that is the reason you can see over here when delta t is greater than 1 minus cj delta x by u naught, corresponding to that value of flux is given as u naught into delta t. What is u naught into delta t? Entire volume. Okay, u naught into delta t is entire volume, but from this entire volume how much volume I need to subtract? This much volume I need to subtract in order to get only this much volume. Okay, so once I subtract this volume, it will be minus of 1 minus cj into delta x. Now if I take a minus common, it will be becoming u naught into delta t plus cj minus 1 into delta x. So that is the flux over here to the right face. Is this point clear? All are clear with this point? So this is nothing but a simple geometry. Okay, so first you have estimated how much is the total volume entrapped, and then you identified how much volume was actually in only the previous cell, because whenever you are estimating the flux, you have to estimate only the portion which is traversing in the next cell. All are clear with this point? So that's why this is now value of flux. Why I am not writing flux for j minus 1 by 2? Please tell me. Because for j minus 1 by 2, every time flux coming from behind is 1. So it will be always positive. So it will be always u naught into delta t. So that's why I am not writing it. It will be as it is. Okay. So if I implement this equation, what will be my solution now? You tell me. For the slug problem. The problem which I defined earlier, slug problem. What is slug problem? This slug is traversing in rightward direction. So if I implement this formulation, what I will be getting? Based on this formulation, my solution should be what accuracy? 100% accuracy? Is this one clear? Okay. In this slug problem, if I implement this type of flux calculation, what I will be doing, because what it is doing, exactly whatever the its basis of this scheme is coming from the exact movement of the interface. Okay, so that's why for one dimensional advection problem, this scheme will be giving me 100% accuracy. Okay, so what you can do, you can give a try for that particular problem. You can implement this flux equation into the solver, and based on this, if you solve, you will be finding always it is giving you the 100% accuracy. Okay. Now what you need to do, your problems will not be always one dimensional. Okay, in reality your problems will be two dimensional, three dimensional. So what you need to do, you need to extend this solution for multiple dimensions. That is our next step. Is this one clear? Because from the basic understanding, it is clear that if I use the volume of fluid approach for flux calculation, in which first we calculate the normal and then we define the volume fraction along the normal, and then based on the actual geometric transformations, if we estimate the flux, we will be getting 100% accuracy for 1D cases. Okay, but now we need to extend this scheme for the multiple dimensions. When we are extending it for the multiple dimensions, then how much accurate is it? So here you can see that this is your actual interface. Okay, so say this is your actual interface profile, and in this actual interface, this is my fluid 1, this is fluid. Okay, if you have to represent this using the scheme which we discussed in the previous case, what I need to do, I need to represent each partial volume fraction in terms of what? Either lines which are parallel to horizontal axis or lines which are parallel to the vertical axis. Okay, so the very first extension of this scheme, 1D scheme, what we discussed in the previous case for two-dimensional interface, was performed in such a way so that in each and every cell which contains the fractional value of the volume fraction, instead of using the single line, two lines were used to define the interface. So one horizontal and one vertical line was simultaneously used to define the interface. Is this one clear? And after this, what was done? Solution was first performed in a single direction. Single direction means all the lines which are having normal along x-axis, first advection equation is solved for all these lines in a given time step. Okay, so if advection equation is solved for all these times in a given time step, then all these lines will be occupying their position in the new cells, next cells. Is this one clear? Depending upon the velocity field. And after that, again the advection is performed for all the vertical lines in upward direction through the same time step. Okay, and after that, again at new step we got these multiple lines, and these multiple lines were nothing but representing my interfaces. Okay, so in this way you will be finding that instead of appearing as the proper curves, the interface will be appearing some stepped functions. Is this point clear? So geometrically interface will be appearing something like a stepped arrangement in each computational cell. Is this point clear? Rather than having a proper curved shape. All are agreeing to this point? So in this way, what you will be finding, you will not be able to define the precise curve, but you will be able to tell that which cell is containing the partial value of the color function. Okay, for traversing the large, for traversing the interfaces which contains the large or macroscopic interfaces, this type of solution works well. But if you have to consider the, say, pinch off of a jet in the form of a small droplet, so in these scenarios, this will be leading to irregular breakups and unphysical breakups of the interfaces, and ultimately we may not be able to capture the extremely small scale phenomenon very precisely. Is this one clear? Then after this, one new scheme was proposed, in which it was decided that let us not use the combination of the horizontal and vertical lines in a single cell, but instead of this, only either we will be using horizontal line or we will be using the vertical line. How to decide which type of line we have to use? So for that purpose, first, normal to the interface was calculated in each computational cell. Okay? And after deciding normal to the interface, the selection of the horizontal or vertical line was selected in such a way so that this line is oriented, normal plane to the line is oriented close to the direction of the normal. Is this one clear? Have you understood what is the next approach? Next approach is, here we are trying to choose the direction in which only use a single line in a cell, but we will be using that line in such a way so that it is closest to the direction of the normal. All are clear with this point? So this type of approximation is known as SLIC, which is known as simple line interface calculation. The second approach is known as SLIC, simple line interface calculation. And this approach is specifically the extension of SLIC, but this method is given by Hart and Nicholas. So typically this is known as Hart and Nicholas volume of fluid method. Okay. And in this case, the point is very clear that first, depending upon the normal direction, we will be choosing whichever is the close horizontal or vertical representation, and we will be using that particular line. And after that, we will be marching the solution in each direction depending upon the interface velocity. Okay. Though the expectation was that, because this was the original scheme and this was the modified version, so expectation was that this would give better interface profile, but it was found that in terms of breakup and the joining of multiple interfaces, this scheme worked very bad. Okay, so it was giving the large number of false pinch off and the unphysical behaviors during the breaking and formation of the interfaces. Okay, so then the next scheme was developed, which is called as PLIC. Okay, what is PLIC? Line interface calculation. What is done in this case? In this case, you can see that instead of defining the horizontal or vertical lines, inclined lines are defined. Okay, so here you can see all these lines are inclined, and these inclined lines are chosen in such a way so that these perfectly follow the direction of the normal. Is this one clear? So each and every line, so say here normal was in this direction, so this line is placed in a plane which is normal to the direction of the normal. Okay, here normal was in this direction, so this direction line is chosen in such a way so that it is normal to the direction of the normal. So in this way you can see that the interface appears, though again it is in the form of what? Stepped lines. Okay, but still it will be closest to the actual curve of the interface what we have. Is this point clear? And one important point you need to consider that whenever we place a line in a computational cell, we have multiple options, because normal has only given the direction, but in this direction this line can be close to the top, it can be close to the bottom, or it can be somewhere in between. So how to decide the location of the line? This line location is selected in such a way so that it covers area equal to Cij into delta x delta y. Okay, so whatever the total area of the cell is there, with when it is multiplied with Cij, that will be giving you the fraction of the area covered by fluid 1. So that particular fraction should be actually represent in a particular cell. That's how the location of this particular line is selected. Is this point clear? Now, after you have used this type of approximation, what we need to do? We need to calculate the velocity in the direction normal to the interface. That means Vn, and based on this Vn, then we need to further advect this line. Okay. Once I will be advecting this type of polylines, what will be happening? Say there is a line something like this. If I am advecting it, and my grid structure is like this, when it is advecting, it will be giving fluxes in multiple cells and in the multiple directions. Okay, so here we need to follow even more complex geometric interpretations in order to estimate the fluxes in the neighboring cells. Is this point clear? So here computations will be becoming a little bit more complicated. So how it will be extending to multiple directions, and how we calculate the normal direction using the volume fraction data, and after that how we put this line at what distance, what are the mathematical formulations of all these parameters, that we will discuss in the subsequent lectures. Okay. And one important point you have to consider here, that whenever these multiple lines are drawn, it is not always true that two lines are actually joining each other. So there can be gaps in between the multiple lines once you zoom in at the microscopic level. Okay. However, these type of irregularities at the interface can be easily controlled once we refine our grid. So if we refine our grid to the sufficient level, then all these type of errors can be avoided. Is this point clear? So there are large number of interface calculation methods. Okay, this is our volume of fluid, and in this volume of fluid, what we were doing, this volume of fluid is many times is also called as geometric WOF. Okay, because here all the computations and interface representations we are doing based on the geometry. Likewise, there is one other parallel version which is called as algebraic WOF. Okay, so till now whatever we are discussing, that is about the geometric representation of the interfaces and advection using geometric representations. So this type of methods which captures the interface in this grid itself, these are called as front capturing methods. So all these four figures are under the category of front capturing method. Then there are other set of category of the methods which are called as front tracking methods. Okay. So typically what is done in a front tracking method? In a front tracking method, on the interface boundary, you can see these black colored particles are placed. So all these are called as surface markers. Okay. So these surface markers are placed on the interface. Now what will be happening on this interface, whenever we will be calculating the velocity of all these surface markers will also be calculated. And then we will be solving some equation for the surface markers, and these surface markers after time delta t, say these have gone to the next time level. Then by just fitting a polynomial curve in all the surface markers, we can actually define the equation of the interface. Okay, so that is, this approach is called as front tracking approach. Front tracking approach is having certain disadvantages. One of the disadvantage of surface markers is that if your interface is lying in the stretching regime, what will be happening? Say here marker velocity was like this, here it was like this. So after some time you will get one marker is here, other is here. So distance between the markers is very, very large. Okay. So because of this large distance between the markers, there can be some inaccuracies. To avoid this problem, some of the front tracking methods, instead of surface markers, they use volume markers. So what is done in case of volume markers? The particles which are placed on the surface, the particles are also placed in one of the primary fluid. These are not placed in both the fluids, but these are only placed in the primary fluid. And now if interface will be deforming, it may happen that when it is stretching, of course some fluid from the inside has to come to the boundary, then only interface mass conservation will be satisfied. So once that fresh fluid from the center is entering to the boundary, then you will be finding that some new particles from the center will be coming close to the boundary, and this way your interface reconstruction will be becoming easier. Okay, because when the distance was large, then it is not very clear whether to join this curve or this curve. But if your number of markers has come from volume to the surface, then you can easily draw interface using all these forms. Okay, but again with the volume markers, this issue of stretching of the interfaces can be resolved. But again, these methods have issues when we are having the complex interface shapes. So it may happen that, say, if your interface shape is so intricate that it is entangled in itself only, now all these are your particle locations. Can you identify whether you need to follow this curve or you need to join it like this? It will be very difficult for you to take a call. Okay, because ultimately, whenever you are drawing it with corresponding shape of the interface, then it becomes easy. But mathematically, ultimately what is happening? You do not have the actual shape of the interface. You only have the positions of the particles. After position of the particle, you have to decide that in which sequence you have to fit polynomial and then represent the interface. Okay. So under this scenario, this becomes actually challenging, but still there are some solvers which employs front tracking methods, and for certain type of problems, these are sometimes even helpful also. Okay. All are clear to this point? So, but again the difficulty comes if you assume that, say, you have one bubble and behind that one another bubble is also coming up. So in this case, the markers of front and markers of back can get confused and you may not be able to properly represent that where is your actual interface profile. Okay, so there are certain types of problem for which all these methods have limitations. So you can see that the computations of multi-phase flow, though there are many advanced methods have been developed, but still the methods are again in the development stage. Okay, because every time our interest is to improve the accuracy, make the method simple and decrease the computational time. So considering all these objectives, people are still developing different types of methods for even for single phase flow problems and the multi-phase flow problems. Okay, so maybe we'll stop at this point and we'll discuss further. There are some other techniques of interface advection such as level set, phase field method, etc. So we will briefly discuss about these in the next lecture, but our major interest will be only on the volume of fluid method in this particular course. Okay.